So thanks, Yuval. It's a wrong guess. There is I apologize. There is no Nash equilibrium in the talk today, but actually there will be at some point. There is PPAD in the slide. No. This is for the people at the recording. It's not for you. Yeah. Think about you are here just now. You're watching this talk, but this talk is going to be on YouTube, and your kids and your grandkids and your great-grandkids are going to watch it decades from now, and you can tell them you were here for my talk. Okay, great. So a little bit of a high-level outline of what's going on in this talk. In the first part of the talk, I'll tell you about an actual theorem I'll tell you about the theorem that we almost proved. This is joint work with Sohail and Muhammad. And I'll also mention a related paper with Amin. And the second part of the talk is going to be about the fantasy that I have. So it's a lot of theorems that I have no idea how to prove. It requires some background, but I don't have this background. But hopefully some of you have some of the background. There will be some. Yeah. Okay. So please. But very important for both parts of the talks. Please ask a lot of questions. You did a great job in Michal's talk this morning. So keep it up. Good. So first part of the talk, complexity of approximate maximum matching. Okay, it's a very simple problem. You have a very simple graph, 5 by 5 bipartite graph. And no weights on anything, no weights on the edges, no weights on the vertices. You want to find the maximum matching. What's the maximum matching in this graph? What's the size? 4, 5, 4, 3, 2? Okay, it's 4, right? Okay, so this is the maximum matching. You cannot do 5. This is 4. This is a maximum matching. And there is a Hopcroft-Karp algorithm from half a century ago. I looked it up on Wikipedia. These are the running times. So if you're okay with a decent approximation, you can do this in almost linear time. It's pretty efficient. And for this talk, I will focus on dense graphs. And you'll see in the second part of the talk why I particularly care about dense graphs. But for dense graphs, let's talk about, so we think of m is roughly n squared, and all the degrees are large. So this is the complexity, roughly n squared time. Okay? But what if we have a really large graph? A really big graph, big data, huge data, etc. So we want something faster than n squared. Okay, and when a small remark is that when we start talking about very large graphs and we want something that runs in faster than the size of the object, we have to be careful with the representation of and we're going to talk about the adjacency matrix. Almost everything I'll say also makes sense in a adjacency list, but let's think about the adjacency matrix for now. Okay, so. Even if you're okay with approximation, there is nothing you can do in sublinear time if you want to return the matching. One example is the graph is just a random perfect matching, and then to find even a constant for every vertex to find with its neighbor, you have to query a constant fraction of the vertices on the other side, and there is no way to return a good matching. Okay, so let's relax what our goal. So instead of actually returning the matching, I just ask how big is the matching? Approximately how big is the matching? Okay, so our goal is to estimate the size of the matching, or there is something else called the local computation algorithm, and I saw some of the experts on this LCA here earlier. So a local computation algorithm says something like this. There is some matching, and I'm going to ask you for vertex v, where is it matched in this approximately optimum matching. So here is vertex V, and the algorithm has to tell me, oh, it's matched to X. And maybe I also ask about U. So this is vertex U, and I'm asking again where it's matched in the matching. And the answer has to be consistent, so the algorithm is not allowed to say that U is matched to X. The answers have to be consistent. Okay, so our goal is to find a matching. Okay, sorry, so we cannot find a matching. Our goal is to either estimate the size of the matching or have a local computation algorithm, so there is some matching that's consistent with, and we're going to ask a vertex, and we're going to get the answer about the vertex's neighbor in approximately maximum matching. Yes, question?
The LCA gives is like it's a matching, or it's like maybe an almost matching. It might say, no, U is not connected to anybody.
So we're looking for so the question is what kind of actually I won't repeat the question, but I'll say, again, explain.
It's a perfect matching.
No, okay, so yeah, okay, Yuval, yeah. So we're not looking for a perfect matching. I'm looking to match as many vertices as possible. Even in this very simple example right here, right? I couldn't match C and W. C and W still get unmatched. I'm trying to match as many vertices as possible. Yeah, it might say it's not matched. No. Yeah, in local computation algorithm, it might say this vertex doesn't have a matching.
And the consistency is with respect to the same matching, right?
Yeah, yes. So there's in the local computation algorithm, there is some single matching, and all the vertices all the responses have to be consistent with the same matching. Yeah.
What's the difference between an LCA and just knowing a matching?
So if you want to return the entire matching, this is completely impossible because you have to say for every vertex where it's matched. The LCA, I'm just asking where is V matched, and I might ask in a different server. I might have a different server, and I'll ask the different server where is U matched. And the answer that I give you for the question about V and the answer that I give you about the question about U have to be consistent, but maybe I don't need to know where everyone is matched.
What is the LCA allowed to do? Is it allowed to query a neighborhood of radius something?
So we'll talk about the running time, yeah. So, very simple, I just care about running time.
So if on one side there's more than square of the vertices of the other side, you could just take a random neighbor.
N vertices on both sides.
What?
There are N vertices on both sides. Amir?
Is there a shared randomness in samples?
Yes, there is shared randomness. Okay? Good. So our goal is to think of estimating the size of what you can think about the local computation algorithm as a motivation. And even in this relaxed model, it's impossible to have a multiplicative approximation. So think about an empty graph versus a graph with one edge. This is either 0 or 1, and distinguishing between those, I have to query almost all the edges in the adjacency matrix. And we'll talk about this example later. Okay, so 1 edge versus 0 edges, there's nothing you can do, right?
But for dense graph, might be possible.
For dense graph, maybe you can do more. So we're going to talk about multiplicative additive approximation. So we are also allow. So we're going to allow a little O of n additive error. Okay, so now we understand what we're trying to do, and there has been a lot of work in the local computation algorithms literature on what to do with sparse graphs. In sparse graphs, there's a lot of work on this question in the LCA literature. Okay, anyway, let's talk about dense graphs. And in dense graph, what we know is that they're in near linear time, you can estimate the size of the maximal matching. So you can estimate the size of a matching that you cannot add any edges to, and this is a 1/2 approximation to the maximum matching. And then we have a paper in upcoming SOTA that breaks this 1/2 plus 1/2 barrier. We can get the 1/2 plus a little bit in almost linear time. Yeah, Pravesh.
Is this like for some epsilon and epsilon prime, or for every epsilon there's an epsilon prime?
For every epsilon prime, there's an epsilon. But yeah. No, this is very exciting. We actually used kind of the harness assumption that there is no such algorithm in another paper, and then I was like, no, it can't be that hard. And, yeah. Anyway, and now very exciting. We can get not just like barely beating half. We can actually get almost 2/3. But it's not near linear time, but it's non-trivial speed up over n squared. And finally, if you make the kind of reasonable assumption that the graph is bipartite, we can even break this 2/3 barrier. So you can get even a little bit better than 2/3, but it's not very fast. It's a little bit better than n squared. So I see in the back it's hard to read. So it's we get a 2/3 plus epsilon approximation. In running time is a little bit subquadratic, so n to the 2 minus epsilon, assuming the graph is bipartite. Yeah.
All of these previous results are for.
Yeah, everything else works for all the other results work for general graphs. Yeah. I mean the lower bounds even for bipartite graphs, but the results.
So actually, since you're pausing this slide, the half approximation, isn't that somehow easy because I only need to get a maximal matching?
Even estimating the maximal matching is it's an amazing paper. Yeah.
If we put epsilon equals a third in the last line,
No, so there is some in the last line. There is some epsilon where we can do this. Yeah, but otherwise, yeah. No, not for every epsilon. Yeah. Think of epsilon as a very small but constant. Okay, so you know I've been working this for not a very long time. People have been working this for over half a century, but I've been working this for several months, and just like every time you know my collaborator said, oh, you know, 1/2, it's this crazy to be, you cannot beat 1/2. We thought about it for a while, and then we got 1/2 plus epsilon, and there's like 2/3 plus epsilon, and it just felt like everything you can, you know, those algorithms are complicated and it's messy and there's a lot of work, but it felt like the algorithms just keep getting better and better and better and better. And what I'm really excited to tell you about is that we can actually prove some harness result. Okay, so we can prove that if you want to beat 2/3, I told you can beat 2/3 in subquadratic time, but you need at least n to the 1.2 time. Okay, and I apologize. This is a little bit of a lie, so it's very convenient. So we actually wrote the proof for adjacency list model. Adjacency matrix, I think we know how to prove, but you know, for the purpose of this talk, you won't see where I'm. If you catch me where I'm lying, then I'll be very happy, and you should be very happy with yourself. But yeah. So
what's the assumption here? What's the harness assumption?
So there's no harness assumption. This is a query complexity. Yeah. This great question. Okay. So there's no harness assumption. This information theoretically you have to query the adjacency matrix or the adjacency list n to the 1.2 times to beat the 2/3 approximation. Question? Yeah.
Sorry, maybe I'm misreading, but so the time doesn't depend on epsilon?
So there exists some sorry, for any epsilon, any constant epsilon, you need almost n to the 1.2.
But it could be that 2/3 exactly is possible.
Yeah, it could be the 2/3 exactly is possible. Yeah. Question about the statement?
and if you replace 2/3 by 9/10, can you prove the n to the
Excellent question. So yeah, we're thinking about it. We have no idea, but maybe you'll have an idea by in 10 minutes you'll see the construction and you can tell me if you what happens when I replace epsilon by. Okay, good. So okay, so this is exciting. It's the first superlinear lower bound on this problem, and you know the interesting thing here is that when you have more than linear time, you can actually the algorithm will actually see some of the edges in the good maximum matching. So we're you know trying to distinguish a case where there is a perfect matching and a matching of size only 2/3. And if you have more than linear time, the algorithm actually see some of the good edges in the maximum matching. So you have to make those edges kind of look like bad edges, indistinguishable from bad edges. On the other hand, we need the yes case. If we want harness of approximation, we need the yes case and no case to be far from each other. Right, so somehow the good edges are really inherently different from the bad edges, yet they're indistinguishable. And this is something that, yeah, every time I was trying to prove harness for this, it very confused me. So let's do this together and see how to do this, okay? Okay, here's the first attempt. This is going to be the yes case, the case with perfect matching. So I'm going to have, this part is actually going to be shared in all the graphs are going to have this structure. So there are going to be some B and S vertices, and the B and S vertices have a perfect matching. And now the question, what happens with these A vertices? In the yes case, there's a perfect matching between the A vertices, and there are also edges between the B vertices. We don't need those edges, but they're there. This is the yes case. So in the yes case, there's a perfect matching. In the no case, we'll replace those green edges. We'll have red edges from A to B vertices. And those edges are useless for matching, because if we want to match the B vertex, we can either match it to the A vertex or to the S vertex. So we cannot make everyone happy. The maximum matching in this graph is only size 2/3. Yeah, for now. All of them are A, B, and S are all the same size.
This is a complete clique?
So for now, no, just a matching. Yeah. So A to B is just a matching for now. Good. So we have a 2/3 harness of approximation, right? Okay, it's a 2/3 gap, but it's not hard to distinguish, right? Like it's very easy to you take you see if the graph has a path of length 3. If yes, you're in the yes case. If no, you're in the no case. Okay, so let's try to make it a little harder. We'll add more edges. So this is going to be oops. Okay, yeah. So this is going to be we'll make we'll add a lot of edges between the A and B vertices in both yes and no case. Both in yes and no case, there are a lot of edges between A and B vertices. For D is going to be n to the 0.2 eventually. Okay, and now when the graph queries an edge, it's most likely one of those A to B edges that appear in both cases and don't tell us anything about the matching. Okay, so we're making a little bit of progress.
Why don't you get a large matching? Do you have the greedy random graph also in the green case, in the yes case?
Yeah. So So the greedy random graph is in both cases. In the yes case, we already have a perfect matching. In the no case, we just have more A to B vertices. It doesn't help us, right? We need A to A edges to get the bigger matching. Okay, yeah, question in the back.
So when we add this random graph between A and B, then why can we introduce larger matching by like some bad luck?
Because so the question is when we add this random graph between A and B vertices, how are we sure that we never introduce a larger matching? And the point is that as long as there is nothing connecting the A to A vertices, every B vertex can either get matched to an S vertex or get matched to an A vertex. So either the S vertex or the A vertex stays lonely. Okay, so this is harder now, right? Because when you query an edge, it's most likely an edge that has nothing to do with the matching. The B vertices and the A vertices, most of they look pretty similar. They just have a bunch of edges. Amir has a yeah. So I'll give you the S vertices for free. It's still hard because you query a B vertex, and you don't know. No, so okay. So in the hard, this will be hard even if I give you the S vertices. I'll tell you which are the S vertices. Ah, great. Yeah. What if you find a B2B edge? Yeah. Yeah, that's a good point. We don't need the B2, or we'll add more B2B edges. But yeah, so you can think of having some B2B edges even in the no case. That's a good point. Yeah.
So if you give me the S for free, why cannot identify B by the neighbors of S?
Yeah. So the idea is you can identify B vertices, but it takes you a pretty long time to identify a B vertex. Sorry, I'm giving you the I give you the S vertex. The S vertices are not for free. I confused. So in this model, you can get the S vertices, but you pay like linear time. Yeah. Sorry. So yeah, not for free. Sorry. Yeah. Yeah. No. It's faster than linear time. It's n over d time, right? In n over d time, you can distinguish the degree. Yeah.
Distinguish whether it's an S vertex or not is based on the degree.
Yeah. So the S vertices are relatively easy to distinguish. They're not completely for free, but they're relatively easy.
Their degree is also the same as this, then.
Wait. It's difficult to distinguish the degree in the matrix
Yeah.
model. In the adjacency list model.
You have to. So in the adjacent list model, you have to do something a little bit different. You just add a bunch of kind of make everyone's degree larger or something. Okay, but anyway, these are all small changes. There is kind of a more inherent algorithm here that's distinguishing and will be important to keep in. These are all good points. Here's a more annoying distinguishing algorithm. Look at a random path of length order d, and ask: Is it possible they went from some B vertex to an A vertex? So in the yes case, because we have the B2B edges, and especially the A to A edges, it's plausible the path went from B to A, even though it has even length. But in the no case, it's very important that I don't have those A to A edges. So it's if I start at B, I go to A and then B and then A and then B and then A. So they really look different. Okay, so let's fix this again. What's a natural fix? Right, we want to add a bunch of B2B edges. Good. So it's going to be like a smaller degree, but good. So now we have B2B edges. Let's make it pretty large. So the degree is going to be epsilon d. The B2B edges is a degree epsilon d random graph, whereas A to B is the degree d. So there are more edges in the A to B, but only by a constant factor. Okay, and this actually makes it easier now to distinguish. Does anyone see the algorithm? So now after I did this, the A vertices and the B vertices have different degrees. And I can look at for an A vertex. I can look at its neighbor, see if one of them has the wrong degree. So it takes me 1 over d tries to find an A edge, and then the time to estimate the degree is only d over n. So I can do this in linear time.
So, Aviad,
Yeah.
instead of adding a random deregular graph between A and B, what if you just don't make it regular? Like maybe have degrees vary between d over 2 and b.
Okay, so Pravesh is suggesting instead of making these regular graphs, random regular graphs, making it regular with some variation, I think something like that could work, but it turns out it's not ideal because you still have like the mean is going to be different, and so there is still a simple fix for this, simple in hindsight at least. So here's another attempt. So we're just going to add more B and S vertices. Looks like this. And now this instead of a regular graph, it's going to be a biregular graph. The A vertices are going to have higher degree in this regular graph than the B vertices, and that evens out the degrees. Okay, does anyone see the? So now it's not 2/3, 2/3 plus epsilon because we added. Even in the no case there is a bigger matching. Okay, does anyone see the distinguishing algorithm now? No, because you have the B2B edges. So this bipartite, this parity thing, yeah, the B2B edges are now in both cases. So the parity thing breaks.
The new vertices have low degree, no?
No, sorry. So this is just a bad drawing. So these are just look exactly like the rest of the B vertices. So they match everywhere.
How much are you adding? Can I just check this?
Just to make the degrees even. So you want the B vertices to look like the A vertices. This is all about. It's hard to distinguish B vertices from A vertices. So you add as many as you need to make the to at least give them the same degree, right? That's the basic thing to make it hard to distinguish.
So you want to count how many nodes are in B or S versus A, right?
But the point is that it's hard to distinguish B and A vertices. Okay, yeah, it seems like there's going to be another algorithm, right? And we can't find one, so now we might think, oh, maybe we finally got this construction that works. Okay, so just to recap the construction, the basic thing that we had is either we have edges from S to B to A in the no case, or we have this S to B matching and A to A matching. So in the S case. And then we add those A to B edges to make things difficult. And then we add the B to B edges to break this parity argument. And then we add the extra B and S vertices to fix the degrees. And the good news is all the algorithms that we came up with seem to fail. None of you caught it. And now we want to analyze any possible algorithm. Okay, so I'll give you a super high level overview of how to do this. I just want to show you, like, you look at this, right? We started from this. Even now, you look at this graph, and the A vertices and B vertices they're obviously different, right? Like in the S case there is a matching from A to A vertices, and these are like A to B is very dense, right? But the algorithm cannot distinguish between A and B vertices. For me, it's very surprising, but okay. So now we want to prove indistinguishability against every possible algorithm, and notice that the queries that the algorithm makes can be adaptive, so the algorithm can see something and then decide to query a different pair of vertices. And the algorithm will see some of the AA edges, but the algorithm will just have a hard time distinguishing between A and B vertices.
So the low bound is for deterministic or randomized?
Randomized algorithms. So this is a concrete distribution. So now you prove a lower bound for the deterministic algorithms.
Probably there's nothing you can do which is better than n squared.
Say that again?
I assume that for deterministic.
Oh yeah. Deterministic. There is a very simple lower bound. We'll talk about deterministic later if we have time. Okay, I'll try to give you a high-level overview of the analysis. There are a couple of seats next to Muli and Dor if anyone has a hard time seeing the slides.
What are the algorithm querying?
So this is a JSON. So the actual analysis that we have written down is for a JSON list, but let's pretend it's a JSON matrix. So the algorithm queries a pair of vertices, and the oracle tells it whether there's an edge between them or not. A great question. I want you here for the second part of the talk. Okay, let's get back to this later. Okay, so the first observation is that as far as the algorithm sees, the graph that it's querying is basically a forest, or what the edges the algorithm discover will never form any cycles. And here's why we picked a degree where this n to the 0.2 comes from. So we let the degree be n to the 0.2, and the algorithm makes n to the 1.2 queries. And I want to tell you the algorithm never sees any cycles. And look, at any point in the algorithm, it made q queries, and each one has a roughly probability d over n of being an edge. So the total number of edges it discovered is roughly n to the 0.4. So now there are n to the 0.4 vertices that have any edges incident on them. So there are n to the 0.8 pairs of vertices that have any edges incident on them. And so out of those n to the 0.8 pairs, probably none of them have another edge between them. None of them share an edge. So we expect that if we ever query a pair of vertices that already have some edges incident on them, the answer is always going to be no. Good. So basically, as far as the algorithm is concerned, it queries, it gets lucky and finds some x and z that maybe have an edge between them. And then it might look for neighbors of z, maybe finds w, maybe finds neighbors of w, etc. But it can never, if it's going to ask about z and y, for sure the answer is going to be no. Okay, so let's say that this is the way the algorithm discovered discovered those edges. And when it starts from x, as far as it knows, x can be either an a vertex or a b vertex. It's approximately a 50-50 coin, right? There are a few more b vertices, but it's almost 50-50. And z, x's neighbor, is also approximately uniform a and b, but it's very correlated with x, right? If x is a, then z is probably b, and if x is b, then z is probably a. And w is also correlated with x, but a little less, because there are some b to b vertices, b to b edges, sorry. But if I have a very long path all the way to this vertex v at the bottom of the slide, the label a to b, whether v is a or b, this is a random variable that has very little correlation with x's label. So the correlation decays exponentially with the length of a path. So this is the second key idea for the analysis that we call correlation decay. That if you look at vertices that are far apart, whether they're A or B is almost independent. Okay, the third important idea is to have this kind of proof by induction. And I want to say that the algorithm never makes a lot of queries that are close to AA edges. Remember, AA edges are the important edges that distinguish yes case from no case. And I want to say the algorithm never makes a lot of queries close to AA edges. And here's the intuitive inductive argument. Let's say we haven't recognized the AA edges so far. So the next query that the algorithm makes, we saw some AA edges, but we don't know these are AA edges. We saw a lot of edges. The next query the algorithm makes the algorithm can't pick close to AA edges because it has no idea where those AA edges are. I mean in this path, right? Because we have this correlation decay, right? If x to z is an AA edge and you query something here, it doesn't help you distinguish whether recognize that x to z is an AA edge. Close in the forest that the algorithm discovered. Sorry. So the algorithm has no idea where the AA edges are. It can't make a lot of queries next to the AA edges, and then it still has no idea where the AA edges are. Okay, this is the third key idea. There are a few more ideas in the proof. I encourage you to read the paper. Actually, this is, if you read the paper, you can read a few more key ideas for the proof for a adjacency list model. The adjacency matrix is harder. You should read the paper after we write it. But yeah, QED. So we prove the theorem, right? Good. I want to recap the first part of the lecture. So our goal is to estimate the approximate maximum matchings. We have new algorithms. So we can beat 1/2 in near linear time, and we can beat 2/3 in non-trivial fast. And we have this first superlinear harness of approximation. And this is the idea for the construction. Okay. Now they told me I'm allowed to talk for over an hour. I don't know if you can possibly listen for over an hour. So let's take a 30 seconds break. Get up, stretch. Get up, stretch. I need you all focus. This is the part where I'm going to start blatantly lying. Also, if you're sitting in the back, this is your chance to move forward. Muli went back so he can steal his seat while he's grabbing a snack. Okay, you can sit down. You can sit down. That's enough snack. Yes, you'll see.
The low bound is for adjacency matrix or adjacency list?
So what we proved is adjacency list. I think I know how to prove adjacency matrix, but
Somehow the first step was for adjacency matrix because you said that if you query n to the power of 1.2, you get n to the
yeah. So the adjacency list.
the opposite, no?
Yeah, in the adjacency list you can modify the construction a little bit. Just add like a bunch of vertices that are connected to everything. And then this makes the adjacency list slower. You have to sort of go very deep in the list to query anything that's actually relevant to the graph.
So why does it go for adjacency matrix?
So the hard thing about the adjacency matrix is that you might learn something from when you query the pair and you got to know there's no edge there, and you might learn some information from that.
What if you change it from choosing D neighbors in general to probability to choose with probability B over N?
This is not the regular graph. So the graph is expected degree D. Yeah, but still.
Would it be helpful for the lower bound?
Yes, it helps analysis it makes analysis cleaner if we think of exactly the regular to think about expected degree D. But still, in the adjacency matrix lower bound, the fact when you query a pair of vertices, you might learn something from the fact that there is no edge there. And now you have this huge, you queried, these pair of vertices, you have an entire graph of no edges that you've seen. You've seen a lot of no edges. And kind of bounding how much you learn from that is more complicated. I think we know how to do this, but.
So in particular, if the adjacency list is sorted, the lower bound doesn't hold.
If the adjacency list is sorted, the lower bound, and you can have random access query to the adjacency list, then then the lower bound doesn't hold. So yeah, there are different kind of variants in the adjacency model, but I'm told this is a standard one that we're using. Anyway, let's talk about the second part. So the second part, it's stuff that I'm not really sure I understand. I learned from it. I talked to a bunch of smart people. They told me a bunch of stuff. I'm going to say some nonsense. The nonsense is completely mine. Good. Let's start. So here's. Oh, it's it's a heart, you know. Like, yeah. Okay. No, they're gonna be greater than 3 nonsense things now. Okay. Good. So. Oh no. There is no upper bound. Okay. Good. Okay. Great. Okay. So there is a conjecture I want to tell you, and there's a challenge, and you have until the end of lecture for the challenge, and I want to get there so you have time for the challenge. Okay. So here's a meta problem. You want to compute distance between structures. So one example is Earth mover distance. So you have two sets in space, in some space, and you want to compute the minimum cost matching, minimum cost perfect matching between those sets. Apparently, it's used in there's something called the Wasserstein GAN. Wasserstein is another name for Earth mover resistance, and it's very important in some applications, machine learning, all that stuff. Another example that I like very much is edit distance. So now you again want to have an optimal matching between DNA sequences, but there are some constraints. So because of the way mutation work, if you're matching one nucleotide to the other one, you want this to be monotone. So it's not exactly the stuff, but it's again some kind of matching. And there is something called RMSD, which is basically the distance between a folded protein. So AlphaFold about a year ago released this like amazing data set of all these folded proteins, and now you have a new protein. You want to know what's the most similar protein that you can synthesize in the lab, and you want to find something that's very close in this distance. And here it's again there is some constraints on matching. There is also some global 3D rotation shift you care about. And there is something called dynamic time warping. It's used to this something with robotics applications. It's not exactly matching. It's almost a matching, but it still falls in this same flavor of problems. Okay, so here's what we know about these problems. They're very important. Lots of applications. Lots of applications. Okay, so. This is a theory fest, so we don't care about that. But what we know is that they can be solved exactly in polynomial time using dynamic programming. But assuming this strong exponential time hypothesis, you cannot solve them in n to the 1.99 time. So you really need the quadratic time. And inherently, all these problems look at matchings, and the strong ETH lower bound embeds this example that we saw earlier, one edge versus no edges. Though we said is you need n squared time, n squared queries to the adjacency matrix. So you embed this into these problems, and the SETH lower bound is essentially embedding this hard instance of matching. But in terms of approximation, these problems are all wide open. There's been a lot of progress in recent years, and we still have a very poor understanding about how hard it is to approximate them. This is kind of maybe a depressing way to end the slide. We don't understand anything. So here's it seems very hopeless. So here's an inspiring success story. Graph diameter. We had a similar story where exact is SETH hard. You could do this in n squared time. And then in recent years, there's been amazing progress, none of this by me. where we have this very clean picture, where the blue is where you have, there's like a trade-off of running time to approximation, and blue is where you have algorithms, and red is where it's SETH hard, and there's green where you're not known to have an algorithm, but it's not SETH hard, assuming n SETH, the non-deterministic variant of strong ETH. So there's this very nice picture, and I have this fantasy that one day we can have similar pictures for problems like air distance and earth mover distance, etc. Good. So here's a very nice paper by Wood and Bakrus. And what they said is they thought about, can we possibly prove harness approximation for edge distance? What would it look like to prove harness approximation for edge distance? And they said one edge versus no edge is SETH harness is not going to help. It's not going to be harness of approximation. By the way, it's not in this paper, but it also doesn't rule out fast quantum algorithms. So quantum people also care about this, maybe. And one challenge is that we need better understanding of show harness approximation for matching problems. So I gave you one example of a harness approximation of maximum matching, unstructured maximum matching in the first part of the talk. In this paper, they said that for deterministic algorithms not only can they not distinguish between no edges and one edge, they can distinguish between no edges and a lot of edges. So you get harness of approximation, but that's only for deterministic algorithms. And the second challenge is that we want to go from a harness of this abstract matching problem on an abstract graph to harness of these actual metrics that we care about. And I want to break this into two challenges. The first challenge is I got some questions in the first half about unconditional versus conditional harness. We need some harness assumption, right? Unless we prove P not equal to NP, to say this is hard, we need some harness assumption. And the second challenge is if we start from an abstract graph, we want to somehow embed it into a concrete metric. And I'll focus mostly on challenge 2.1, and if time, I'll get to 2.2. Okay, but this is a high-level picture. We want to prove harness approximation for those things. First, we need to, the vision is to first prove query complexity lower bound of matching, and then think about this embedding challenges. Okay, so what kind of a harness assumption are we looking for? And are we going to need a separate harness assumption for each of those problems, etc.? So like I said, strong ETH inherently is about this one edge versus no edges. It's not good for harness approximation. And even when we perfectly understand the query complexity, we're going to need some harness assumption. Otherwise, or a great breakthrough on P versus NP. So hopefully we have this great breakthrough soon. But until then, and it would be nice to have one unifying harness assumption instead of saying, oh, I have this query complexity problem, and for this problem, I assume it's hard, and therefore at a distance is hard. I want some kind of a canonical harness assumption. And there's been in literature this kind of very nice work, very nice idea, vision, that maybe you can just say, query complexity is hard. No, I give you some succinct embedding, like a succinct representation of the oracle, like a circuit or a Turing machine, and I give you this succinct representation. So like white box versus a black box. And there is something called the black box hypothesis that postulates that running time with a white box is roughly at least as large as the query complexity given black box access. So this is similar to lifting theorems in communication complexity if you've seen them, but we wish to have this for algorithms. Okay, so this black box hypothesis, there's a lot of work on this. It would be very nice if we had something like this. It would unify a lot of harness assumptions that we need all the time, like P not equal to NP, or this variant of strong ETH, or someone, so evaluate promises would be a Nash equilibrium. So if we want to say that PPAD is hard, under this black box hypothesis would be hard, and a lot of other things. I want to make this remark that for fine-grained complexity, if you want to distinguish like linear time versus n squared time, or n to the 1.9 time versus n squared, we need some non-traditional parameters. For example, white box axis is not necessarily like polynomial time Turing machine. It might be something different. And the greater than, we should be a very fine grained, so up to like n to the low point. But anyway, there's some fine print details about this. But for now, let's keep things high level and ignore this. There are bigger issues to tackle.
So Aviad,
Yeah.
do we know what might be considered as counterexamples to the black box hypothesis?
Great question. Thanks, Bhavesh. So, yeah, the really like big thing here is this is false, okay? And what might be considered a counterexample? So here is a really annoying counterexample. Okay, so I give you an oracle, and I want to ask like some question about the oracle. So one question I can ask is like, can you implement this oracle by a small circuit? Now, if I give you white box access to a small circuit, the answer is obviously yes. If I give you black box access to a random oracle, it's pretty hard to answer this question. There is also another obstacle that I'll get to hopefully, about even if I promise to you that that the black box oracle is implementable by this is more interesting, I know. Okay, so even if I promise to you that the black box oracle is implementable by a small circuit, for promise problems, this is still false using this impossibility of full obfuscation. Okay, so this assumption is super false, or this hypothesis is super false, and my goal is to come up with a plausible variant of this hypothesis. What do I mean by plausible? First of all, I want it to be plausibly useful for ruling out these like unrealistically fast algorithms for edit distance, say, or Earth mover distance. And my second goal is I want it to be plausibly true. And I have a modest benchmark. None of you refute this until I finish talking, and I at least make it off the stage safely. It seems like a very modest benchmark. Last time I gave a version of this talk, I didn't make it. Elon Yogev refuted my hypothesis. Okay, it's great. So now you have a challenge. Okay, pay attention. I'm gonna give you a variant of this black box hypothesis. Let's see if you can refute it by by the end of my lecture. This is your challenge. Good. So there'll be a prize for anyone who does this. Okay. So let's talk about this first obstacle. Can this oracle be implemented by a small circuit? And what some papers do is they say, okay, I'm just gonna measure the black box query complexity against oracles that can also be implemented by a small circuit. So this is white box and this is black box, but it's black box, but I promise to you that the black box is also implementable by a small circuit. The annoying thing is that now the query complexity bound that we prove, I know how to prove query complexity bound on random graphs or something. I don't know how to prove query complexity bounds to hold when the oracle is implementable by a small circuit. It's actually, for total problems, it's actually impossible. Total search problems is actually, there's a really nice result. It's actually not, it's impossible to, the black box query complexity is always low when the oracle is implemented by a small circuit. There are some provable bounds for quantum also. Okay, so this it breaks my query complexity lower bound, so it's not it doesn't satisfy the plausibly useful criterion. Okay, so here's another idea that I had. I want to talk about think of like an analog of NP. So I want to say that in yes cases, there is a witness. Okay, so every yes instance, there is a witness that proves that this is really a yes witness, and the verifier can make sure that. So I show the verifier. So even in the black box, which is hard, right? In the black, I want to say problems are a hard black box. I can open some of the black box queries, and then the verifier can be convinced, can be efficiently convinced that this is a yes instance. And my intuition is that if you want to prove to me that this oracle is exactly implementable by a small circuit, you have to open all the queries to make sure that the circuit exactly matches on everywhere, the oracle everywhere. And this is not going to be an efficient witness. So I'm trying to rule out this, can this oracle be implemented by a small circuit? And my proposal was to require this efficient witness. That you can just, if in the S case, if it can be implemented by a small circuit, I'm going to show you some of the oracle responses. I'm going to choose some of the oracle responses to show you, and that will convince you. Right, and this kind of rules out, now you can check that this oracle is really implemented by a small circuit. Sorry, this is a good time for questions. Any questions? Yeah, Amir. Oh, okay, yeah. Okay, so I'll repeat it again. I'm keeping some of the parameters vague on purpose. Okay, so yeah, okay, good. So I wanna have some kind of variant of this black box hypothesis that will be plausibly true. Good. I have this annoying kind of question, like if the problem I'm asking is, can this oracle be implemented by a small circuit? This is very easy in the white box model, right? Because I have to give you the small circuit. But black box, it's hard, right? Yeah. Not necessarily smallest, but I ask you, is there some small circuit that's okay? And I give you some small circuit, as opposed to like a random. If I give you a random oracle, there is not even a smallish circuit. And what I want to suggest is I want to say that I require that in the yes case there will be a witness proving that this is really a yes case. And now if you even if your oracle no, in the black box model, even in the black box model, in the white box, maybe everything is efficient, but even in the black box model we assume is hard, there is still an efficient witness.
For both cases.
In the yes case, like NP-like. So in the yes case, you no, but I think yeah, maybe like query version of NP. So maybe it's yes and no case, but in the yes case, you can there's an efficient witness. Okay, so I'm trying to rule out this kind of question, and now we ask, is this oracle implemented by a small circuit? How can you convince me that the oracle is implemented by a small circuit, right? Without showing me all the oracle responses. Okay, Amir? Good. So no, this is the part to pay attention to, really. Okay. So the natural attack on this is you want to ask, is there a circuit that agrees with the oracle and random input? Right. And the like in the white box is going to agree everywhere, but if I give you a random oracle, even agreeing with like on the average input is hard. And the caveat with this kind of attack is that the black box query algorithm that's trying to distinguish, it's not clear where I have to have the random inputs in a way that hide it, like the random if the random inputs is kind of caked into the problem, the black box algorithm can query the oracle on those random inputs and then enumerate all the circuits and kind of see. And here's a very nice kind of workaround that Elon you showed me. So you're going to ask, is there a small circuit C that agrees with the oracle O, and the input oracle O applied to the description of C? And the tricky thing here is that if O is a random oracle, then for every, if I want to check if C is a good candidate, I have to check it at a random point with seed C. So for every circuit C, I have to check it at a different place. So that's hard to do in the black box. But in the white box, I give you a circuit C. Of course, it's CFC, it agrees with C, and it's very easy. Okay, now here is my new my new hypothesis. Sorry, so here's the intuition. I want to say that even with white box access, the one thing that we still have to like kind of fight this kind of annoying question is that even with white box access, we only know one circuit. But if there is some circuit, there are going to be many circuits. And I somehow want to use this to separate like this kind of annoying contrived questions from natural questions that correspond to, say, matchings. Okay, here's my new hypothesis. Challenge for you all. You can refute it. So I want the black box query complexity to satisfy the following desideratum. So I want to say there exists a small circuit that implements an oracle. Maybe it's not the exact same oracle, but the oracle that's implemented by a small circuit has the same set of solutions or same set of witnesses. So if you're asking, like, is this oracle implemented by a small circuit? Well, if I give you the random oracle, there is no solution to this. So there isn't a circuit that's the same. Here's an example. If you think of part one of the talk, okay, I'm going to fix the good matching. I'll hard code it into some efficient representation. But the random edges, the masking edges from the B to A edges and the random B to B and B to A edges, I'll draw those. In the black box case, I'll draw these really at random. And white box case, I'll have some pseudo-random way to draw them.
So you mean computationally indistinguishable?
No, I mean exactly the same set of solutions. I want to give you a lot of time for this challenge. I think I have 5 minutes left, right? Okay, so if you solve this over lunch, if you refute this over lunch, it's also this is a good time for questions about this. Dor, does the hypothesis make sense?
Still trying to understand what it means.
So requiring that the entire oracle is represented by is implementable by a small circuit is too strong. The query complexity breaks. The query complexity lower bound breaks. But I just want to require that there is a small circuit that implements has the same set of solutions. So if you think of this example, the matching is still, there is just one perfect matching, the same matching. And now those kind of masking edges, the A to B edges, are just there to confuse you. Those can be, in the query complexity, allowed to be uniformly random.
What if it's with random oracle? So I'm adding another object here. Random oracle, both signs have it. I mean, you can do processing, whatever you want.
Yes, but in the later I want to embed this into. I really want this to have. I want to really have actually have a small circuit, because I want to encode this small circuit as an eddy distance problem, or earth mover distance. So random oracle, I can't encode the random oracle. I want to actually have a small circuit. So I want to somehow assume that when there is an actual small circuit, the problem doesn't become easier.
What's the solution? The solution to what?
So I ask you, for example, in matching, right? A solution is a maximum matching or a perfect matching. Say, I'm asking you, does this graph have a perfect matching? So the solution would be a perfect matching. And
The input to some problem?
so the input to the problem is the oracle, right? Or the graph, right, which is described by this oracle. And the solution is say a matching, right? So the same set the set of perfect matchings has to be the same in the query complexity in the black box. Yeah, but you're allowed to use a different graph, right? Because the random graph is not going to be represented by a small circuit, or with a few random bits, right?
But maybe here you actually have more solutions because you have more perfect matchings because of the B2B.
No, you need the B2S for the perfect matching. Yeah. Okay, good. So you can keep. Okay, should I let you think about? How about this? I'll show you 2 more slides. I'll show you 20 more slides in 2 minutes, and then we can think about it over lunch and let me know if you're for this. I'm very interested in this. So. Okay, so good. There is this other thing. Even if the circuit even if the oracle is truly implemented by a small circuit, promise problems breaks. But I really care about promise problems because I want to say yes and no distributions are far. And here I don't have anything super elegant. I just want to say I'm allowed promise problems, but only promise problems where the promise is like a Hamming distance. And so if in terms of like you're close to yes, if you're kind of close to both yes and no, you're allowed to answer anything. It seems plausible, but. Okay, so yeah, I'm happy to talk about this offline. It's still interesting. Yeah, there's a lot of parameters to discuss. But the main thing I want to say is I want to have this like middle ground where the query complexities with respect to instances not necessarily exactly implementable by a small circuit, but the same set of solutions with a small circuit. Okay, I have good. So two more slides, and I know we're all hungry, and I've been talking for too long. So one, we want to have lower bounds on the query complexity of matching. So by the way, we only did this for this like unstructured any matching, but for eddy distance, for example, we care about monotone matching. It's still very open. And 2.1, we have some hypothesis that we can have some small representation, like a small circuit, and then we can transfer the query complexity to some kind of white box lower bound under some harness assumption. But 2.2, we actually want to embed this, say, circuit or something as like 2 DNA sequences. And the typical strong exponential time hypothesis harness result, the embedding is this kind of representation. The vertices in the matching correspond to vectors, and there is an edge if the 2 vectors are orthogonal, if their dot product is 0. And we had some work on something called the distributed PCP framework to embed this orthogonal vectors problem with some harness of approximation. The parameter is still very far from tight, but we get some non-trivial harness of approximation, whereas the original kind of orthogonal vectors embedding gives you no harness of approximation. There is also another line of work that says that for problems like eddy distance and dynamic time warping, you can replace this this very simple representation of are the vectors orthogonal or not. You can replace them with some do they together form a satisfying assignment for like a small circuit or a small branching program. And it's not entirely clear so the parameters here are still pretty weak, and also it's not entirely clear if we can combine these together. So even in terms of embedding this gives you a flavor of what I mean by embedding this. But even if we have the query complexity lower bound, even if we have the right hypothesis, it's not obvious we can embed this in a metric with hardness of approximation. But so that's still a challenge. Okay, so this is the recap of part 2. This is the fantasy that I have, and these are kind of the challenges that we have there. And it seems like a lot of formidable challenges. Maybe one like anywhere where these challenges are kind of break, there's an opportunity for algorithms. So even if it seems like a crazy fantasy, maybe we can get algorithms, which would not be as satisfying as hardness results. But if that's what we get, then what can you do? Okay, this is the talk on it. I apologize for lots of open questions. Sorry for going over time. I'm happy to chat over lunch.
Maybe time for a quick question? If not, then you can ask Aviad over lunch.
Thanks.